had that on my mind. And there we go. Okay. So now we're recording. That's fine that we didn't record the other. So we're starting with Ryan sharing his GeoGebra file on similar triangles.
Can you see it?
I can't yet. Yeah, there it is.
Okay, great.
There it is. Yes, I got it. Can everybody see it?
Yeah.
Yeah? Okay, good. Go ahead.
We have a triangle ABC in the left.
Right. Use your mouse to point to it as you're talking.
Okay, right there.
Yeah.
It's the little one.
Right.
So I started out with a dilation, and I dilated triangle ABC with a center point on A with a scaling factor of first, actually, I took the distance or the length of BA and compared and the length of QN right there, this one, and so then I could find the scaling factor, and once I did the dilation and it prompted me to do the scaling factor, I just divided NQ by the length of BA. Then it gave me triangle A prime, B prime, and C prime, which is this bigger one. I translated it.
Okay, wait a minute. Logan, you clear on that?
Yes.
Okay, go ahead.
So then I just translated it the triangle A prime, B prime, and C prime by C prime to T, I believe.
Yeah, that factor there.
And it gave me this, the double prime triangle. And I did two ways. The first way, I did a rotation to get it to where the triangle was actually mirroring and making a kite. And then I reflected that over the line QT by the angle that was given from B double prime and
yeah, you can point to the angle.
This angle. That was the first time, but then I thought it might be a little bit easier if I just reflected it over this line segment. Because it is the bisector of B double prime, T, and Q for that angle. And then I reflected this triangle over there. And
yeah, you got it. We all clear on that? I want to point out something that was a confusion before, so that was good. Notice that what Ryan just did was he said he could do something in two transformations, a rotation and then a reflection, or he could do it in one, a reflection. And when it says in the homework what transformation is this, and it names two, what it means is what single transformation will accomplish that. It doesn't mean describe the two transformations. It means what single transformation will do that. So Ryan just showed that instead of doing a rotation and then a reflection, you could do it with a single reflection. Okay? Good? All right, good. Thank you. All right, so that was the first thing. I want to say quickly, and you might want to just take a note on this. You should we've been doing everything online virtually through GeoGebra, which is good, I think, but sometimes it's also useful to have graph paper and a pencil and, to do it physically as well. Usually when I teach this, I started physically so people get a sense of what's going on and then go to this. This is good, but I'd like you to bring graph paper to class, and if you can get tracing paper or what they call patty paper, some geometry teachers use bulk patty paper, which is like what they serve hamburgers on, but they sell it specifically for math, actually. And it's just tracing paper. And what that's useful for is rotation, to really see the rotation, see the steps. So if try to find some. I don't want you to go out and buy it. It's expensive, but try to find some at your school. See if somebody has some tracing paper or a patty paper that you can use. You don't need very much, but that would be useful. Okay. All right. Right. The other little detail I want to mention is sometimes on the assignment document itself, there is a little work to do. So when you turn in your homework, if there is work to do there, then turn in that document as well with with whatever items require something to write. So I just wanted to remind you of that. And then I did put 2 files in. I don't want to do that now. I'd rather do something else. But I just want to tell you that under the class today in eCollege, I put confirming congruence and confirming similarity files that I made just by, in the congruence case, taking a triangle and moving it around, and it's good practice. So you can practice if you have trouble with this, moving one onto the other with a series of isometries, a sequence of isometries, and a confirming similarity file in which you would do something just like Ryan did today. Okay, enough said on that. Now what I want to do is, and then the transformational geometry axiomatic system, we'll do more of that on Friday. And I want to tell you that Friday's quiz, I'm going to give a quiz on Friday. If you guys want to if anybody wants to make up the last quiz, that's the only time I'm going to do a retake on this, then do it by Friday. Okay? Go in and I approve the retake. You can see your grade on the, and I'm going to find out more about making more of the grades visible today from Ms. Obe. But you can take the quiz by Friday. The quiz on this Friday is going to be review. Okay, so just covering what we've done before, and it'll be relatively quick. Okay, now what I want to do is go over. This is the crux of today, and I want Walter is going to lead this. On the January 16th homework, Ryan. Mm-hmm. I want you to get up your coordinate puzzles file.
The one that you commented on?
Yes.
Okay.
And this is practice. This is what we're all going to do. So we're going through a dry run here. And then I want you to share your screen on that coordinate puzzles file. And we're going to go over 1 and 2. And Walter is going to lead this. Okay, it's cooking. There it is. Okay. And can you zoom, zoom in a little bit on that? There you go. All right, good. Thank you. All right, so number 1 is just what I was talking about. Okay, so I'm hearing an echo. So let's see. Okay, when I talk, can you hear an echo?
No.
Okay. Good. All right. So it says after a transformation, the coordinates of the vertices of the image are that. So there's the image, the pre-image, and the image, and you can see what Ryan did is he said one translation and one reflection. Okay, but after a transformation means one transformation, not two. That's just what we talked about. Okay, so. Okay, Walter, here, I'm talking too much.
All right, so what do you want me to do?
I want you to help
All right.
Ryan see what he should do in this case.
All
So,
right.
sort of how should he get started with this?
Okay, so I guess the first thing is like, what do you notice that's different about A prime and A and B prime and B and so forth?
Just the x values are opposite of each other, or they're the
All
opposite.
right, so that suggests a reflection, and um, I think one reflection is enough for this exercise. So, do you know like what line you reflect it by?
No.
All right,
Do,
so um,
do you have
I
graph
think
paper? Just a minute. I'm sorry to interrupt. Do you have graph paper with you?
Me? Not
Yeah.
not with me.
Okay. All right. That would be good for next time. Go ahead, Walter. I'm sorry.
Alright, so in general, if you reflect something across the y-axis, that just takes the x-coordinate and multiplies it by -1.
I do. I do have graph paper.
Okay.
Okay, yeah, across the y-axis, right?
Yeah,
Or,
across the y-axis.
okay.
So what
So
would the
the
one? Sorry. Go
so
ahead. Shut up. I'm
the
going to shut up.
only transformation that I had to do was reflecting the triangle over the y-axis in this one.
Yeah, you could draw it
Okay.
out and see how that works.
Okay.
So Ryan, I want you to get in the reviewing toolbar on your Word file. You know how to do that? Or the reviewing
Yeah.
tab. Okay, so get in the reviewing tab, turn track changes on.
Let me download it and pull it up into where that was PDF.
Oh, okay. Yeah, do that. Okay, we'll wait. Because then I want you to add the correct answer after what's written now. I don't want any of you guys to delete anything. Just add.
The review, right? The review tab.
Yeah.
Uh, what do I do after that?
You see where it says track changes?
Okay.
And then turn that on. Turn track changes on.
I think it's on.
Okay. Okay. Now just go after where it says after a transformation means one transformation, not two, and click your and go to the next line if you want or whatever, or just write the correct answer now.
Okay. Is that fine?
Yeah, that's fine. Yeah. Okay. Good. I'm curious that it doesn't show the nice colors that mine does, but I'm not sure why. But it does show the thing on the left that bar that you've made show more. Okay, so we'll figure that out. I don't know. It's not worth it, but play with that. Play with that next, in the future.
Okay.
Okay, look at number 2.
Okay.
So scroll down to number 2. And it says, after a different transformation, the coordinates of the vertices of the image are that. So use your graph paper and then you say, again, two different things are needed. So I want Walter to help you find the one thing. So I'm going to be quiet now.
Okay. I'd start by drawing this new triangle, because once you draw it, it becomes pretty clear.
Is this just over the reflected over the origin?
Yeah. But I guess reflecting across a point isn't really a transformation. So what do you usually do when you fix a point and you have a transformation around it?
You rotate it?
Yeah.
Okay.
How much do you rotate it by?
Oh, 180. Right?
Yeah. Exactly.
Okay.
Yeah.
Okay. So
thank you, Walter. So write the correct answer there.
But you have to specify which point you're rotating it by.
Wouldn't that be the origin
Yes, it would.
in this case? Okay.
Yeah. So therefore, in general, a rotation around the origin by 180 degrees, just takes each x and y coordinate and multiplies it by -1.
Okay.
Center isn't the word you want.
Okay. Point of rotation?
No, what's that point? What's 0, 0 called?
The origin?
Yeah.
Okay.
Good.
Okay.
All right. Okay, that's it for that file. And you have other things to fix, but I wanted to get that clear, and that's how you do it. And that's how I want all you guys, after I comment on your homework, that's what I want you to do, is go back and fix. All right. Open the Intro to Symmetry file. Same day.
It's coming up.
Good.
This one.
Good. And we're going to do number 3 first.
Okay.
Okay, Walter, I'll give you a chance to look at it. And my comment was many of these are not line symmetric.
Okay, so the way I think of line symmetric is that if there is a line across this letter, such that if I fold the letter across this line, you get the two halves to line up together.
Yeah.
Do you see what I mean?
Yeah.
All right. So, using that knowledge, is C line symmetric?
Yes.
Okay. What about H?
No.
Okay. Yeah.
So C.
What about I?
No. At least not horizontally.
Yeah, there's no horizontal line of reflection, but is there a vertical line of reflection?
Yeah. Or
Okay.
Yeah, and don't worry about the little font issues. Just
yeah.
yeah. Question.
So the vertical line in this one would be thinner than the eye itself, right?
Yeah, a line,
Okay.
yes. A line theoretically has no thickness.
Okay, great.
It's an abstract line. Okay, slow down, slow down. Okay, Walter, talk.
Um, oh, I personally think M and N have line symmetries, but I mean, you have that little thing where you, but like, that's not really an issue, I guess.
Okay. Yeah,
Yeah.
and I have questions about because N, that little thing that sticks up is important.
Okay.
Is it okay then? In that
Yeah,
case, N doesn't
I
have
think
the
it
symmetry then.
is.
Okay.
Okay. And so N and M don't. Okay. S wouldn't. Um, T would
Yeah.
if you just.
All right, I think we can stop. You have the idea.
Okay.
Okay, you get it. Okay, the next thing is F. So capital F after the numbers. Yeah. Okay, so yeah, scroll it up a little bit more so we can see F. There you go. Okay. Okay, so stop. So it says, what is your definition of the word symmetry? And it says, yeah. All right, so I want Walter to help you fix that. So see what you said. Now this is symmetry, period. The word symmetry, not without reference to a particular transformation.
So, symmetry probably isn't just limited to line and rotational symmetry, but there's probably a symmetry for all these transformations. So
Yeah.
basically, a symmetry is basically if something is symmetric, then there exists a transformation such that the transformation maps the pre-image to the pre-image itself. So the image is basically the exact same thing as the pre-image.
Okay.
Well said. Okay, so write down something like that.
So like when you apply the transformation, nothing actually changes.
So what kind of thing is symmetric? What is a what?
Just an object?
Yeah, okay. Or a figure or something you draw. So start with that. Let's say a figure. A figure is symmetric if A, not the. Yeah, okay. A figure is symmetric if, and then finish it.
If the pre-image can be mapped onto uh, the image.
Yes. Yes. The image by what kind of transformation?
An isometry?
Yes.
Okay.
Excellent. Okay, good. Okay, let's look at G. And Walter, I'll let you do this.
So some of these letters don't have line symmetry. Can you find which ones they are?
S and Z.
Yeah. I think that's it.
Yeah, good. Lox, bagels and lox. Have that for breakfast. Uh, that's kind of fun. I have a little tip for you, which is interesting. Autocorrect drives me nuts sometimes, but if you do Control Z, I guess, on a PC, or you undo the last thing, then it undoes the autocorrect,
Okay.
which is nice, a nice little trick. All right,
Thanks.
enough for this. Enough for this file. Good.
Mhm.
You can close this one. And then I want you to open, now, when I said TGA 2.4 transformations, and what that comes from is I helped write a unit for professional development for teachers, and it's transformational geometry A, and A was supposed to be the first one, and then B will be the harder one that's not done yet. And it was just module 2, section 4. That's just a reminder to me of where this comes from. Okay, so TGA 2.4 transformations. should be somewhere. Can you not find it? There you go.
Okay.
Good. And this we want to go over as much as we can once you get that up. Yeah, delving deeper into transformations. Okay. And yes, and yeah, blow it up a little bit. And okay, and so I can see that my comments are in a different font, so that's good.
Okay.
All right. Yeah, thank you. All right, A is more or less isn't a big deal. Let's go on. Yeah. Okay, B seems to be okay, so keep going. And 2. Okay. Yeah, okay. Okay, Walter. Take over here. Yeah. And actually, Ryan, you may be able to fix this now based on the work you've done since. So which of the 3 basic isometries map lines to lines? And Walter will help you.
Is it all of them? Because or is it wouldn't it be all of them? Because they all preserve collinearity.
Yeah, Walter, response?
Yeah, that's one way to think about it. But all right. Yeah, it is all of them.
So correct that. Okay.
I guess another way to think about it is like, if you reflect a line, do you get another line back?
Mm-hmm.
If you rotate a line about a point, do you get another line back?
Yeah.
If you translate the line, do you get a line back? So yeah. Okay.
And so this one's all of them as well, right? Because
Yes, it is.
yeah.
Okay. Logan, is this helping you too?
Yes. Yeah, it is.
Good.
Okay, so for C, suppose that the line you're trying to reflect is not perpendicular to the line you're reflecting it by.
Okay,
Would they be
so
parallel?
So it would be reflection and a translation?
Translation, sure, but does a reflection make it so that the image is parallel to the pre-image?
No, not all the time. Right?
Sorry, what'd you say?
Not all the time.
Yeah, it's not all the time
Patterns?
because if you reflect a line that's not perpendicular to the line of reflection, like you're gonna get an angle.
Okay. Okay, yeah.
Hmm.
So, uh, translation. So, translation's the only one, and reflections occasionally.
And even then,
Yeah,
if you reflect a line that's perpendicular to the line of reflection, you're just gonna get the line back. So it's not really parallel. So just translation.
Okay.
it could be parallel to the line of reflection also. But think of y equals x reflected in the y-axis. Do you get a line that's parallel to? Is the image line parallel to the pre-image?
No.
Yeah, no. The pre-image has what slope? Y equals x has what slope?
1.
Yeah, and when you reflect it, you get y equals negative x, right?
So you got a -1.
Yeah,
Okay.
slope is
Cool.
not preserved. So the reason I did B and C is that they're different. Uh,
Hmm.
and so, yeah, so I want you to really realize the difference there. Preserving parallels does not mean B and C have different meanings. That's the point.
Okay.
Okay. All right, go on. Keep going. Yes, that's right. Keep going. There. To the graphs. Yeah, down a little farther. Okay, up a little bit. Yeah. All right. So Ryan claims that, and this was a stretch factor of 2, a horizontal stretch with a stretch factor of 2, and there's something wrong with it. So Walter, can you help Ryan fix this?
Yeah. So by the definition of the stretch thing in the paragraph in part B, it says that in this particular case, the x coordinates are all multiplied by 2, but the y coordinates are unchanged.
Okay.
So, in the pre-image, what is that? That's 2, 6, right? So that should be stretched to 4 comma 6 because the x coordinates are multiplied by 2. So you
Okay.
just do that for all the coordinates, all the vertices, sorry.
Yeah, you don't have to fix it now in there. Just make a note. Just write a note after image is not correct. Say the image of 2, 6 should be. Just write that for now, and you can come back and do it better later. Good. Okay, great. Excellent. Okay, keep going. Same. Okay, wait. Let me see. Oh yeah. Okay, Walter, look at C and try to help him fix that. And look at my comment.
Okay, so Mr. Douglas says 2 points aren't enough because through any 2 points there exists a line. So you have to try 3 points instead of 2.
Okay. Okay.
Okay.
And
So
then
go
like
ahead.
before you just apply the rule and just multiply each x coordinate by a scale factor of 2.
Right. So just
And
make a
with that
note on the bottom that I need to try 3 points.
Okay.
Okay, good enough. You can go back and finish it later. Let's look at D. See if there is an issue there. Oh, yeah. Okay. We don't need to worry about that. You can look at that later. Keep going. And then you made it was the same error here. So that's all right. Yeah, you see that you didn't move the x coordinates on the left side. They stay at 1. The x coordinates stayed at 1, and you need to move them. You need to double the x coordinates. Okay. So yeah. Okay, that's fine. Keep going. Okay, now we talked about notation.
Oh, that's what I wrote. Okay.
All right. I don't think we need to do anything with that. I'm not sure. Yeah, go back to that for a minute. Let me see that.
The notation?
Yeah, what you were doing. Yeah, okay. Transformation of the function notation. So that's what you wrote? The function notation leaves out the other coordinate. Yeah, I didn't make a comment, so okay, it's okay. Keep going. I'm sorry. Go to horizontal shear, see if there's an issue there.
Okay.
Yeah, keep going down a little more. Hard to move it, I guess.
Oh, okay. So show that the horizontal shear is not an isometry?
Yeah, you need to, yes, your image is incorrect. You have to apply the rule to each vertex. So let's take the example of 1, is that 1,6? Is that correct? Yeah, that one.
Yes.
Okay, so where is 1,6 going to go? Go back to the rule and see what it says. So 1,6 goes into what point?
It moved to 7.6.
Yes. So put down there 1,6 goes to 7,6, and that's not what you have. Okay. So you just really need to be careful about applying the rule. All right. Enough said on that. Okay, keep going. Watch the time here. Okay. Fixed point. Okay, no big deal there. A fixed point is it doesn't move under a transformation. So the pre-image point coincides with the image point. That's what a fixed point is. And we want to get the difference between that and an invariant set. So go down to where it says invariant set and look at what I underlined. An invariant set may or may not have fixed points. Only the figure as a whole must be fixed.
Okay.
So we're talking about a set that's fixed, that is, but each individual point in the set does not have to be fixed.
So the image just has to remain the same?
Yes. So here's an example. Think of the x-axis, okay? And think of a translation 5 units to the right. Okay. Does a translation 5 units to the right have any fixed points?
No.
Okay, Walter, take over here about the invariant set of that. of
All
the
right, so
translation 5 units to the right.
so if we had the x-axis and then we translated it 5 to the right, it was an invariant set, right? So we can generalize this to any sort of line. So if if you have a line parallel to the translation vector and you translate this line by that vector, then you'll get the line back, which is basically what you had right there. So that's fine. Okay.
Okay?
Mm,
Are we clear?
Mm-hmm. Yeah.
But there are no fixed points, but there is an invariant set. And in fact, there are lots of invariant sets. Okay, keep going. I think we're just about done here. Look at the projection part, number 8.
Okay.
Okay. And explain why it's not a transformation. And you said it's collapsed on, it's not possible to have a one-to-one mapping. Okay, true, I said, but better to show by an example that the mapping is not one-to-one. So, yeah, so give 2 points that go on to the same point, and so you'll show that it's not one-to-one.
Okay.
Okay.
So a projection is just like taking a square and then collapsing it down to a line.
Yeah. Can you think of 2 points whose image is the same? Think of 2 points that have the same image.
Okay.
What are they? Give me an example.
Is it like one and one?
1, is 1 point, and
1.
oh, I need a different point that has the same image. What's the image of 1?
It's just a point. 1, 2.
Look again at what it says. U of x, U takes xy into what?
X and 0. Okay. So it'd be just 1, 0.
Yeah, so 1 goes into 1, 0. What's another point that goes into 1, 0?
1, 2.
Yeah, good.
So anything just above it or below it?
Right.
Okay.
Good. Okay. All right, and then yeah. Okay, and you started off B really well, but then that last sentence has a problem. So what's the image of the triangle with vertices? And you said a line segment along the x-axis that begins at x equals -4 and ends with x equals 5. That's great. But then you say a line goes on forever. I don't understand why you said that.
I have no idea either.
Okay. You get rid of that sentence, it's fine. Yeah. Okay. What points are okay? That's good. That's good. C is good. And D, what set of points is invariant? Is invariant lines hard? Yeah. Okay. So think about that. Walter, can you help him with that?
yeah, just okay.
So would it just be lines in the lines on the x-axis, or points on the x-axis?
Yeah,
Okay.
because these points all map back to the x-axis, so the x-axis or y = 0 is invariant.
Good. So write that. Yeah, you could either say points on the x-axis or you could say the x-axis. Either one is fine. Okay? So write that on D, Ryan, so you remember. Ryan, you with me?
Yes.
Yeah. So write that on D.
Points on the x-axis or just the x-axis?
Either way, yeah. Pick one of those and write it. Oh, you got it.
I did.
I didn't see it. Okay. Okay. All right, good. Okay, we're done. We're done with that. It's 9:57. That was the crucial part. All right. I don't know if we have time. Walter, I was going to have you show us how to make a slider. We have 3 minutes. Can you at least start it? Share your screen?
Making a slider?
Yeah.
I'll try.
Okay. Okay. You know what? I think you're right. I think we're not going to have time. But we can do that. We can do that tonight. So if you could kind of set that up, okay? And I'll have you show that tonight. Okay. So we're going to meet at 7 Central Time and 8 Eastern Time tonight. Okay? And I will and just log. I'll log into. I'll open Blue Jeans as a moderator, just like I did now, and you guys log on to Blue Jeans from home, and get Adobe Connect up too. I think that's going to work, and because that's how we can share our screens through Adobe Connect.
Okay.
Okay, we good?
How long will this last?
Good question. Let's say half an hour. Is that okay?
Yeah, that sounds good.
Okay.
Also, I'm not gonna be here on Friday.
Okay. What's going on with you?
I have a Model UN conference.
Oh, okay.
Yeah.
Okay, Walter.
Yeah.
Thanks for telling me. I'll write that down. All right, and I'll send you an email about what to do. Okay. Good enough for now. You guys can log off. Logan, can you stay on? I want to make a separate time with you.
Yeah.